All right, so let's see. Was somebody gone? Nobody's gone, but it's such a great day. I got to record. All right, because I honestly think some of you this weekend are probably going to want to watch it again. All right, so the velocity, absolute value of velocity is the speed. And so now if we do the integral of the absolute value of velocity, okay, from 0 to 4, well, what does that do to the graph? Flips it up. So this part is actually going to flip up like so. So now the area is actually positive 10. All right? And so now 90 plus 10 is 100 miles. That is the total distance traveled. So that's how we get those two distance answers. And this is going to be something very important for us down the road. The integral of velocity is net distance traveled. The integral of speed is total distance traveled, because the speed equation, everything is positive. So all the areas will be positive. So no matter what direction you're going, you're counting and adding that direction. Okay? But when it's negative, when you have velocity, you can have velocity positive or negative, so you can have areas that are positive and negative. And it talks about the direction. So we have already talked about how the area under there is the distance you travel, but now we've kind of even been more specific about it. When you have a negative area, that means you're going a distance in the other direction. So positive distance and negative distance, and then those add up to make the displacement or net distance. So that's what's important about that one. Okay, another problem I think some of you had questions about was 71. Seemed like. Now 71 gives me two functions. The f function was that to x plus x, or 6, I mean. And then the g function was x cubed. Am I right on that? All right. And so what happens here is we get a function that is looks something like this. Is the line. Oh, man. Let's try.
This is such a great book.
I'm so excited. I'm shaking as I try to do this one. All right, and then, because as you know, my lines are usually spot. All right, and so x cubed comes up like so and comes down like so. All right, and so we're supposed to do the area. What they wanted to talk about, the first was just a sketch, I think, right? Sketch the region bounded by, now this is something we'll do a lot in chapter 7, okay? Regions bounded by multiple curves, all right? Which is different than the area under the curve, right? Which is the area between the curve and the x-axis. Now we're talking about a region bounded by multiple curves. And they gave you these two curves and then the y-axis. They said x equals 0, which is the y-axis. So that would be right here. So that would be, so we're talking about this area right here, this blue area. All right? And it makes sense that has an area. There is some number that represents the area of that blue space there. All right? So then in part B, they said, how could you write an integral that would be that area? Because our integrals, remember, are between the curve and the x-axis. Any ideas? Now I know, yeah, go ahead.
Oh, the integral of from 0 to 2 of f of x minus the integral of 0 to 2 of dx.
Because this is the 0.28, and I think I'll help you see it if I draw this a little bit. The integral of, let's do it in black. The integral from 0 to 2 of f of x, that's the line. That's the area under the line. So that would be this black trapezoid, right? And then what would be the integral of the x cubed? That would be this part in here, right? And so what Brenna said, if you subtract the black minus the red, shouldn't that give you the blue? And that's exactly what we're talking about doing here. So the integral would look like this, and you could actually put x plus 6 in here and x cubed in here, that'd be fine. And that would be enough for your answer. Now, one thing I wanted to mention is since we said we could split apart integrals, you can also put them back together. So this, since f of x is x plus 6 and g of x is x cubed, this would be equivalent to the integral from 0 to 2 of x plus 6 minus x cubed dx. Now, the only reason I mention that is it's just interesting to think that if I just gave you this integral, especially before you ever saw this problem, if I just gave you this integral, would you have thought of it as two curves subtracted and do an area? No, what would you have thought of? This one curve, right? And hopefully you had a calculator. Get your calculator. You could get your calculator out. You could graph this thing. It would be one curve. There'd be the area under it from 0 to 2, and guess what that area would be? The same as this blue area right there. It would be a whole different piece of area, but it would have the same value. Just like the area of this room and maybe the room across the hall. They're two different rooms, two different places, but they have the same area. Right? They would have the same value. 3 plus 4 and 5 plus 2 look very different, but they're the same. They have the same value, right? So that's what these integrals are. Remember, we said that. A definite integral is just a number. Now, we're going to change and we're going to put a twist on that today. But a definite integral, like these, are just numbers. They're a fixed piece of area. Okay? And so here's a piece of area, the black area, then the red area. We subtract and we get the blue area. But we can also think about that as this one piece of area here under this curve. And this piece of area be the same as this blue piece of area right there. Okay, so it's important, I think, to just understand that concept. Okay, were there any others in the book there? I want to talk about the packet real quick. But any in the book? Any others in the book? 62? Okay, let's look at 62 real quick. 62 said that you were given an area. Let's make this pi halves. Make this pi. We'll have this go up here to 1. Okay, so we have the sine graph. It comes up, comes back down, right, and so forth, so on. Okay, but what we were asked to do is the integral from, what was it, pi 6 to pi halves of sine x dx. So that would be this area right here. Okay, this red area. Oh, no. All right, from pi 6, here would be pi 6 right here, and here would be pi half. Okay, so this would be pi 6. And so we would have this red area right here. All right, now we don't know what that red area is. We could approximate it. We could kind of count squares. Remember, we only have two ways really of doing areas right now. One would be approximation, and another would be geometry, right? If it's a geometry shape. Well, this is not a geometry shape. Close to a trapezoid, but it's not because it's curved. All right, so we don't really know how to find this area. Well, one of the things we do, we'll do more with this in chapter 6, is we can bound that area. We can say, okay, I don't know what that area is, but I can at least find an area that I know it's bigger than, and I can find an area I know it's littler than, and I know it's between those two areas. If we can narrow that down, then we can get pretty close to the exact area. If you think about it, it's kind of what we did with derivatives and slopes. Can't do slope at 1 point, but I can do slope at 2 points. So if I can do 2 points and make the 2 points get close together, I can eventually figure out what the slope is. It's a little bit the same idea here. Okay, so I told you to go to page 307, and there was a picture there, and it talked about max and min. So if we look at the minimum in this interval, it's right here. So let's do that in blue. So I know that my area is bigger than that area because that is the minimum in that little interval. So the curve has to go above that. So I know my area has got to at least be that big, but maybe more. And then in black here, let's do the maximum. And of course, if we had a horizontal line where the max and min were the same, then of course that'd be easy. The area would be the area. But so we know the area is got to be between that max area and that minimum area in blue. So now it's just, now all they want you to do then at that point is just do the area of those two rectangles. So the black one, the bigger one, would just be a rectangle. So what would be the width? of this? How much is that? Pi, I think it's pi thirds. Well, it's pi halves minus pi 6. We'll do that in a second. Okay, that's the width of this interval right here. And what's the height of this interval? Sine of pi halves, which, yes, is 1. Okay, but that would be the width and the height of that black rectangle. Okay, and we'll work that out in a minute. Now, the blue rectangle would have the same width, so it'd be pi halves minus pi 6. And the only reason I'm writing this out is because they said show that this is a true statement. So that's the width of my blue rectangle. What's the height of my blue rectangle? Sine of pi 6, right? Whatever that y value is. So pi halves, that'd be 3 pi 6. 3 pi 6 minus 1 pi 6 would be 2 pi 6, which is pi thirds. So that'd be pi thirds. And then what's sine of pi 6? Sine of pi 6 is 1/2. So pi thirds times 1/2 is pi 6. And that, I think, is what they said in problem 62. So, and then over here, this would be pi thirds. And we said this is times 1. So pi thirds times 1 is pi thirds. So this integral is in between those two values. That's how we get it. The area of the blue rectangle, the area of the black rectangle. And that's where that goes. Okay? So we don't know how to find that area, but here's a way we could narrow it down. All right. Let's look at the packet real quick. I wanted to talk about number 6 and number 7. The ones I told you could kind of skip. Right? So, number 6. All right, here's the deal. It says g of y equals y cubed. Well, if f of x is just another name for what? Y. Then what do you suppose g of y is another name for? X. And that's exactly right. What this is x equals y cubed. What it is the inverse of x cubed. It's the inverse function of x cubed. So we can do integrals with respect to y, just like we can do it with respect to x. Now, on one hand, we said you could use any letter. Remember we had W and U and T and those other ones in the homework yesterday? So, I mean, it's possible to do that and just think, well, they really meant x. But y is kind of special because usually x's are input, y's are output. So, you know, that's a little bit different deal. But the answer to this problem would have been the integral of y cubed dy from what to what, do you suppose? No. 0 to 2. Because if we're doing it with respect to y, then doesn't it make sense that those two numbers would be y values instead of x values? And they are. And notice the area is not between the curve and the x-axis, but it's between the curve and the y-axis. Now that's going to have practical implications. When we get into chapter 7 and some applications of these areas and these integrals, that's going to be important. Now, what some people have told me over the years is whenever they saw one of those, they just did the inverse, just flipped it around and thought of it as, just thought of this as y, oops. They thought it was easier for themselves to just think of that as y equals x cubed. And they thought of this, in other words, they just turned their paper, basically. And because it would be true that if you graphed this like so, and then did this piece of area right here, that this red piece of area is the same as that other shaded piece of area. And that would just be the integral x cubed dx from 0 to 2. Well, it makes perfect sense because remember when we said we could type it into our calculator, remember the U1 and the W1 and the T1? Calculator doesn't know the difference. If you do dt, dw, du, whatever, those are the same problem. But graphically, they're really not the same. They're the same area. They give out the same value, so it's related to that problem we talked about a minute ago. But graphically, they're really two different things. So I think while it's okay to think of it that way, they really are two different things graphically. And I think there is a point later where it'll be a little more confusing if you always do it that way. So I understand it does work. And so let's just look at 6 real quick. So what do you think 6 would be? 0 to 2. Oops. So it'd be 0 to 2, that's correct, and then it'd be y minus 2 squared dy. Right, and it would be that. Okay, so it's really, again, just a parabola flipped around. Okay? All right, so again, when we get into chapter 7 later, we'll get into some of those issues with those horizontal kind of situations. All right. So, I guess that is all I need to do. So, yeah, this is, I think we'll just let the video run. So everybody's got this document now. So what you need, and you can do this with a partner, with a small group, whatever, by yourself, however you want to do it. So go ahead and get to that document that I sent you. Now I may interrupt at some point and make a comment about something or send you a question. We'll see how it goes. So you can just kind of follow the directions with this. And we'll try to get it wrapped up here by about 1:30 or so we can talk about kind of some things relating to it. Okay?